All right, so let's talk about activating groups. An activating group, by definition, is a substituent that donates electron density back into um, the main molecule to which it's attached to. Now, in this case, that would be the benzene ring itself. And an example of strong activators, the ones that dump plenty of electron density into the ring, are hydroxy substituents, such as the case of phenol, oxo substituents, basically from phenoxide, the conjugate base, and then aromatic amines, such as aniline, especially if the aniline derivative has alkylation on the nitrogen. That's even more, it's a stronger substituent as far as donating electrons to that benzene ring. Then we have what we call moderator activators, the ones that donate, a fair amount of electron density, but not as much as what we see with the hydroxo, the oxo, or the amine derivatives. So those are your anisole derivatives or your ether derivatives for your alkyl, and also your amide derivatives, which is basically like the amine, but you have acylated the amine, turned it into a much more, benign group. It's still activating, but it's not as strong as the regular amine without the acyl group. And then you have what we call weak activators, groups that still donate electron density to the ring, but they do that only to a minor extent. Specifically, those will be just your regular alkyls, methyl groups, ethyl groups, isopropyls, T-butyls, etc. So the thing to keep in mind is that when you do have in your ring a strong activator, you can have multiple electrophilic substitutions occurring on your ring. And even if you're just attempting to make a single substitution, there's a really great chance, especially if you have a strong or moderator activator, that you will undergo multiple electrophilic substitutions. The other thing about it too is that some of these groups, such as the oxo group, the amine group, are basic and they don't really work well under acidic conditions, mostly because the acid will react with the amine or it will react with the oxo group. So those will be situations where you'll have incompatible reaction conditions in relation to the substituent that's present on the ring. So you have to watch out for that. And the thing to kind of notice, and this is almost the dead giveaway that you have an activator, is that the element that is directly attached to the benzene ring happens to have at least one lone pair of electrons, with the exception of the alkyls. The alkyls will be the only ones that don't have lone pairs on that element directly attached to the benzene ring, but everything else, the hydroxo, the amines, the amides, they all have the one electron set, the one electron pair that is right next to the double bond of the benzene ring. So basically, what this all means is that resonance structures are a possibility. And to kind of show you how that works out, let me make the case with the strong activator, the phenol molecule. You have those lone pairs on oxygen, and because those lone pairs are next to an atom that has a multiple bond, you could undergo resonance structures. Specifically, the lone pair can come down here to the carbon, and it can kick out the pi bond of electrons onto the adjacent carbon of that double bond, thus creating an oxonium cation and your carbo anion here on the upper right portion of the molecule. Now, I don't want you to think that this is the most stable form of the molecule. It isn't. The neutral derivative is the most stable version and the best representation of all the resonance structures I'm going to show you. But everything else that I'm going to show you here is going to depict sites on the carbon chain where you have more electron density, and then sites where you have less electron density, which will play a role in terms of the electrophilic aromatic substitution. So if we continue this process, the lone pairs that we have generated right here in the carbon ion also happen to be next to another multiple bond. So we could continue the resonance structure by having those electrons attack the adjacent carbon, and in the process kick out the pi set of electrons to the third carbon in the series. So now we end up with the double bond here on the right side of the molecule and the carbon ion on the bottom portion of the molecule. And just like before, the new and freshly formed lone pair of electrons is next to another multiple bond to its left side. So we're going to continue with the resonance. So we have now electrons moving to the left and kicking out the pi set of electrons to the third carbon in that series. So that now we have a carbon ion on the upper left portion of the ring. And last but not least, that carbon ion can ultimately attack the carbonyl carbon that's been generated right here, kicking out one of those pi electrons back to the oxygen and reforming a neutral species. But what you should realize is that this form of phenol is the Kekulé structure of the original one, right? Notice that one of the pi bonds is on the left side of the molecule. Now it's on the right side of the molecule. They are resonance structures altogether. All right, so what we're seeing right now from all of this movement of electrons is that the ortho positions in respect to the original substituent, right? So the ortho position here on the right, the ortho position there on the left, and the para positions are the ones where we generate the most electron density. In essence, that's where we generate the carbon ions as we go through the resonance structures. And what that ultimately means is that these sites are the ones that have the most electron density. And as a result, these are the sites where if you are to do more than one substitution on the benzene ring, the substitutions are going to happen on this position specifically, ortho to the activating group or para to the activating group. So that's kind of how this kind of starts coming together. And another thing to also keep in mind is that the alkyls, although they don't have the lone pairs to go through all the resonance structures, they do activate the ortho and para positions in a similar manner, but they do so via induction, not via resonance. All right, so what that brings us to is the groups that do the exact opposite, the groups that remove electron density away from the benzene ring, the deactivating groups. So much like the activating groups, they come in three forms. There are the strong ones, the moderate ones, and the weak ones. So we're going to start with the strong ones. The strong deactivating groups are trihalomethane groups. The halogen could be fluoro, chloro, bromo. And this is a good electron withdrawing group. Basically, you will be pumping electron density away from the benzene ring via induction. Another good one is the nitro group, which we talked about in the previous video as far as how to make it. This, via resonance as well as induction, has the ability to withdraw electron density. And then the technically tetraalkylated ammonium version of aniline is also a strong electron withdrawing group by the activator because of the presence of the positive charge that by induction withdraws electron density away from the aromatic ring. Now, other ones that fall under the category of moderate are your sulfonic acid, your cyano group, and your azole substituents. And this could also be ketones, they could be aldehydes, they could be esters, they could be amides. As long as the carbonyl is attached to the benzene ring, it will act as a deactivator. And the similarity among all three of these molecules is that you do have a highly electronegative atom, which is not directly bound to the benzene ring, but instead you have it bound one position away from it. So that is kind of the key to this thing. Lastly, and this is kind of like the oddball of the list, the weak deactivators happen to be halogens themselves, fluorine, chlorine, bromine, and iodine. But the one big difference here is that unlike the other deactivating groups, these are the only ones that actually happen to have lone pairs on the atom directly bound to the benzene ring. Nothing else has lone pairs on the atom directly bound to the benzene ring. So that's going to have an important outcome, as I'll depict momentarily. But first thing to mention is that when you have a strong, moderate, or even a weak deactivator on the benzene ring to begin with, if you do a subsequent electrophilic aromatic substitution, you'll only undergo one more. because these things are removing electron density from the ring, making it less likely for them to, do multiple um, substitutions. Second thing is that in the presence of the strongly and moderately deactivating groups, basically the ones up here, Friedel-Crafts reactions are not an option. This applies to both alkylations and acylations alike. And the last thing that I already mentioned is that with the exception of the halogens, none of the atoms directly bound to the benzene ring have lone pairs, which is one of the key things to notice. All right, so to kind of highlight that idea, I'm going to use the nitro group, and it has to be drawn out completely, right? So you cannot just leave it as NO2. Like, you have to draw it completely with structure, because I'm going to show you right now via resonance how these things deactivate electron density. And what you can see right here is that in the case of the nitro group, you do have that formal positive charge on the nitrogen, which is enough for the pi bond of the benzene ring to move over towards the nitrogen. And at the same time, you break the pi bond between the nitrogen-oxygen segment here on the left side. But what this ultimately does is it creates a carbocation in the ortho position here on the right side of the molecule. Now, that carbocation is next to another double bond. So this is technically an allylic carbocation. So the double bond can move over towards the carbocation and regenerate a new carbocation site on the para position to where the nitro group is located. And of course, the carbocation is next to another double bond, so the double bond can move over to generate another carbocation on the ortho position. And then lastly, you could bring back the lone pair of the oxygen towards the nitrogen, kick the pi bond of the carbon-nitrogen bond back to the carbocation, reforming the aromaticity of the ring. But what you're seeing that right now happening is that with the electron withdrawing groups, the ortho and pair positions now happen to be the least electron dense sites on the molecule. In essence, these are the sites that would be the least likely to behave as nucleophiles. And what that also means is that you're going to basically undergo substitutions. If you actually undergo substitutions in these type of molecules, you'll undergo the substitutions on the meta positions, because those are the ones that have the most electron density, because between positive charge and neutral charge is more electron dense. So, and just like we talked about in the previous examples, even though the trihalomethane and the tetraalkyl ammonium derivatives don't have the option for resonance, they are still undergoing the same type of event via induction. So they work out the same way altogether. All right, so this brings us lastly to the last oddball of the series, right? The weakly deactivating groups, the halogens. Now, the halogens, because they do have lone pairs, they can undergo resonance structures where you bring the electrons from the halogen down to the benzene ring, you create a carbon ion, and you can continue that series over and over. So you go from ortho carbon ion to para carbon ion, back to ortho carbon ion, and ultimately ending on the Kekule structure of the original chlorobenzene. But what you're basically seeing now is that because of the presence of those lone pairs, the ortho and para positions are actually the most electron-rich portions of the molecule. So in the presence of halogens, you will still undergo substitutions in the ortho and para positions, which is to be contrasted from what happens with the strong and the moderately strong deactivators. Now, the reason why this is still considered a deactivating group is because the halogens are more electronegative than carbon. So via induction, they are, in essence, withdrawing electron density away from the carbon. And that inductive effect is a little bit stronger than the resonance effect. But the resonance effect still plays a huge role because it dictates that the substitutions will have to happen ortho or para in relation to the halogen. All right, so with all that being said, I will catch you in the next video where we'll talk about next and different set of reactions that will allow us to introduce more functionality on the benzene ring, the nitrobenzene reactions, the diazotization reactions. So see you then.